introduce our first speaker.
Shall I share screen already?
Sure, why don't you share screen and then we'll just wait until exactly 4 o'clock to start. Yeah, good. Okay, so we are right on time. And the first speaker of this session is Surajit Sengupta from TCIS Hyderabad. And the title of his talk is A Statistical Mechanical Theory for the Origin of Rigidity in Crystalline Solids. Go ahead, Surajit.
Okay, so this is an outline. So I'll start with a very brief background on rigidity and yielding transition in crystalline solids. I'll talk about the established viewpoint and point out some of its flaws. And then our viewpoint will be introduced in two steps. First, I will talk about a droplet hypothesis where we are going to view yielding as a nucleation of stress-free droplets within the body of a stress solid. I'll show that there is some evidence from experiments about this. And then in the second part of the talk, I will talk about an extremely unusual phase transition, which is associated with quasistatic yielding. This is a spontaneous symmetry breaking ordering transition. And this is what is producing these stress-free droplets. And I'll show that there is some evidence for this from simulations. And finally, I will conclude and give some future directions if time permits. Okay, so the usual stress versus strain curve. So for small deformation, stress is proportional to strain. That's Hooke's law. And at some large deformation, at the yield point, there is a small jump in the stress. And that is the point where defects like dislocations, they begin to move. And these dislocations can be actually seen in experiments in transmission electron microscopy pictures, for example, the one that you have on the right. So this is the standard phenomenon that we are going to describe. And the usual viewpoint is that it's all about dislocations, breaking of global translational symmetry in the liquid during crystallization causes rigidity. And so during yielding, you have a lot of defects which begin to move because of some dynamic deepening or unjamming of dislocations. And defects restore translational symmetry. So it creates disorder. So obviously rigidity goes. So it's all about dislocations. So many body physics of dislocations is the key to understanding all phenomena concerned with yielding. Now, this is a viewpoint which is shared by almost everyone in the community, and this also pervades all textbooks in this subject. However, there are a few problems with this viewpoint. Problem number one is that the yield point is not a fixed quantity. It's a function of strain rate. And you can see that this is yield stress versus strain rate. And if you decrease strain rate, the yield strength decreases. Of course, you have to decrease it by orders of magnitude to get the yield point to decrease by just a few decimal places. However, this is seen in almost any material, any crystalline solid, of course. And this is sort of explained in the form of an empirical equation where the yield stress has a rate independent part and the part which is a power law. And this power turns out to be extremely small. So whenever in physics you get extremely small power, like 0.006, you know that there is maybe something wrong with this law itself. So, and this is it's a very celebrated Johnson and Cook formula. Okay, so the second problem is a little bit more severe because crystal rigidity actually violates thermodynamics. How? Suppose you take an ideal crystal which where all the atoms are sitting in their minimum energy positions and you deform the boundary, the atoms are moved away from these positions and so stress rises to resist this deformation and there is a free energy cost to it. However, the atoms can always rearrange in this fashion by putting in lattice slips so that the atoms are again back to their minimum energy configuration. So there is zero stress in this. Okay, and the bulk free energy goes to zero and is replaced by only a small surface contribution coming from these steps. Okay, so this thing has been noticed, this thing has been noticed before, and these papers are sort of our inspiration. So, what is going to happen? And what we have done basically is to convert this into a calculation which can be tested against experiments. So, the droplet hypothesis is very simple. So, we say that there is normal solid which is rigid and it has some stress, and because of some reason droplets of stress free regions grow within the body of this solid. We will call that some M crystal, let's say. So we all of course have a first order transition in the background. The stress in these regions is zero. So you do an energy audit, volume and surface, and then you can plot the free energy as a function of the size of these droplets, and it goes through a maximum, and you can find out the barrier, and the barrier it uh, diverges as 1 by epsilon square. Okay, so this is a very standard classical nucleation theory calculation. So how do you convert that to something that can be compared with experiments? In typical experiments, strain is ramped up at some rate. So this barrier is time dependent. And then you can write down a Kramer's mean first passage time and realize that the yield point is nothing but the rate of deformation multiplied by this first passage time. This leads to a self-consistent equation which can actually be solved in terms of something called the Lambert W function. And this Lambert W function is a monotonically increasing function. It goes to zero when the argument goes to zero. So there is absolutely no rate independent yield point in this formulation. And how does it work with experiments? Here on the y-axis, we have basically the inverse yield point to the fourth power. And on the x-axis, you have a strain rate. And you can see that there is data here. These data comes from several things. So the data on the left are from experiments, and the data on the right are simulations, and there's an 8 order of magnitude gap between them. And this line is from our theory. It just goes through all the data. There are 2 only fitting parameters here. Alpha is an interfacial energy scale, and tau 0 is a time scale. So this thing, it fits the entire data and probably will fail only in this little light pink region where instabilities appear because the barriers are very small, and there is a breakdown of classical nucleation theory itself. Okay, so we have a theory which explains data, but strangely, no knowledge of dislocation dynamics was necessary for predicting the yield point. This is extremely surprising and raises many questions. So, of course, the first question is, what is the origin of this constant interfacial energy? Why is it constant even at epsilon going to zero, where 2 crystals should be identical? Actually, if one assumes that this interfacial energy arises only from dislocations, then you get an expression which gives completely unphysical results. So what happened to these locations? They are actually observed in experiments. What is the order parameter of this so-called first order transition? What is the broken symmetry phase? How does exactly stress vanish in this M phase? Okay, so to answer these questions, we have to actually do something a little bit drastic, which I'll tell you. So the idea is that in all theories of solids, excitations in solids are usually classified as smooth displacement fluctuations, which are phonons, and singular, which is coming from dislocations. Okay, this is the basis for almost all theories of solids. We actually need a different classification, and we classify them as locally affine or non-affine. What is affine? Affine is that you take a circle and you transform it into an ellipse. That's an affine transformation. You take the same circle and you transform it into an amoeba. That's a non-affine transformation. So we go into each neighborhood inside the solid, do a coarse graining of the local normal modes, and project them into mutually orthogonal subspaces, affine and non-affine. Okay, so all these projections are Gaussian random variables with zero mean, because they are, after all, linear combinations of phonons. The susceptibilities of these Gaussian random variables, they contain a lot of information. So the affine susceptibilities, the widths of these Gaussians, are simply elastic compliances. The non-affine susceptibilities, they measure how readily the lattice actually allows nucleation of defects. The fun fact is that dislocations automatically pop out from this formulation under certain circumstances. Okay, so you don't have to keep dislocations separately. So let us look at these susceptibilities of the non-affine displacements in two crystalline systems. One is a 2D triangular lattice, and the other is a 3D FCC lattice. And these are the susceptibilities. You can we have just plotted them as lines. You can see that there is one or a set of degenerate modes which have the largest susceptibilities, so that the local Hessian is very flat in these directions, but of course not completely flat, and it is separated by the others by a large gap. So what are these modes? In the 2D triangular lattice, these modes try to introduce a dislocation anti-dislocation pair. In the FCC lattice, it tries to introduce a stacking fault. Now, these modes are, of course, highly spatially correlated with non-trivial correlations, and which means that gradients, spatial gradients, cost energy. So we have all the ingredients for this theory of yielding, and we are looking at quasistatic yielding here, where we deform the solid, deform the boundary of the solid by an affine strain, and as soon as the solid can put in one slip plane, it does so, and there's a little sort of step at the surface, and you have such a structure where stress goes to zero. Okay, so to describe this, we project all the relative displacements of particles on this soft non-affine mode. And we take this as a fluctuating random variable. We can take it as complex, it doesn't matter. This is zero for before the transition. And as soon as this transition happens, it condenses near the slip plane and it spontaneously breaks local lattice translational invariance. Now, the interesting thing is that the amplitude of this mode is very large at the slip plane, but almost zero elsewhere. So if you were to calculate an intensive order parameter, that goes to zero as 1 by the system size. Okay. Our only innovation here is to realize that this order parameter is actually incommensurate with the crystal lattice, because any wavelength of variation of this order parameter is decided by the shape of the crystal and the deformation. So we treat this as an incommensurate modulated phase. The theory of incommensurate phases, such as incommensurate charge density wave or a concentration wave, is extremely well developed, and there are a lot of papers. So we just simply shamelessly borrow the entire mathematical formulation from these papers. And the only lesson that we take from here is that we have to replace derivatives by translationally invariant gradients, which involves auxiliary fields. These auxiliary fields, the curl of this, it produces internal stresses which produce local deformation that try to restore translational invariance. So this is the only lesson that we need. And then we can write down a Landau-Ginzburg theory. The first part is the homogeneous part. It allows for a first order transition. Then there are gradients, and then there is a term related to the internal stresses. And you have to find out the Euler-Lagrange equations for this. The Euler-Lagrange equation for the order parameter is this. And then when you take when you minimize this with respect to this internal these auxiliary fields, you get a very famous equation called the Kroner's equation that relates a dislocation density tensor to the plastic deformation tensor, which is just the thermodynamic conjugate to the internal stresses. And from the dislocation density tensor, you can calculate a total Burgers vector. Now comes the most important part. The Burgers vector can't be anything. It has to be constrained by the shape of the crystal. For every slip plane, you have a Burgers vector of 1. This restricts the order parameter to a subdimensional domain, which is on the slip plane. So there is a topological constraint which determines the nature of the ground state. Okay, so now we are ready to calculate the free energy of a little droplet. We have to take into account that we are interested in strains which are larger than the strain at which the first slip plane occurs, but it is still small. And to have a droplet, you should maintain that the size of the system goes to infinity, the radius of the droplet goes to infinity, but radius divided by size goes to 0. In this limit, you have a large density of slip planes like this, and you can actually neglect the dislocation contribution altogether and get interfacial free energy over a certain width, which you can minimize and get the minimized interfacial free energy, which is independent of the strain in this limit. And what happens to the dislocations? You have to take Kroner's equation, manipulate it a little bit, the algebra, and you can derive a Laplace equation for the stress. So I have written the Laplace equation for the one component of the stress. You can write it for the other component working on the slip plane, which is identical, and you can see that the stress is expelled within a certain penetration depth. So as the order parameter goes up, as you go inside the droplet, the stress goes down, and there is an interfacial defects which appear at the same time. So although the dislocation contribution to the interfacial energy may be neglected to leading order, it is the interfacial dislocations which produce a stress-free droplet in the first place. Okay, so this is the theory. So now evidence from simulations. So when you go to simulations, this is you have to be very, very careful here, because in simulations you can deal only with finite size crystals. So in finite size crystals, there are several things which happen. First of all, the equilibrium bulk transition, it goes as some A0 by L. If L is small, this is not a very small number. And the lower limit of slip density is 1. So you can't get a very large slip density. And quasistatic yielding, which happens as strain rate equal to 0, is not associated with the equilibrium bulk transition. It is associated with the reversible droplet condensation evaporation transition. Now, this is well known from liquid gas, Ising model, and so on. So what happens here is that in infinite solid, droplets of the stable phase are always unstable, in the sense that droplets lower than the critical radius, they shrink, and droplets larger than the critical radius, they grow. However, if you have a finite system, then you can have a stable droplet. This is easy to understand in the liquid gas context, because in order to grow a droplet of liquid, you need atoms to come from the rest of the solid. However, if you have a finite system, then that is limited. So that sort of stabilizes a droplet of a certain radius. A similar thing is happening here, although it is difficult to understand it directly as in the Ising system. And what this means is that there are colossal finite size effects. And this may also appear in experiments. So this is something that we have to keep in mind. So what it really means for dynamics is that when you write down the free energy of a droplet, there is an extra term which comes from the mismatch of the orientation of the droplet and the crystal with the principal axis of deformation. So this mismatch term, it sort of limits the yield point. So the yield point now does not go to 0, but it approaches a plateau value in this fashion, as you can easily see from repeating the classical nucleation theory argument. So This plateau value, of course, goes to zero as the system size increases, but it goes to zero very, very slowly. So we have done molecular dynamic simulations of standard Lennard-Jones crystals oriented properly using standard velocity Verlet in lamps. And for the equilibrium simulations, we have to do successive umbrella sampling molecular Monte Carlo, because the stable and the metastable states are sort of separated by huge barriers, and normal Monte Carlo or normal molecular dynamics cannot take you from one to the other. Okay, and and we also studied this in the NVT ensemble at a constant field Hx, which is just the thermodynamic conjugate to the intensive order parameter x. Okay, and we can actually constrain this x to various values and calculate the probability distribution of x, and then negative logarithm of that gives us an effective free energy. Okay, so first the dynamics results, and here you can see that for the small systems, the yield point, it veers away from the equilibrium value, and it goes to a plateau. And here, here you see the equilibrium results given. They go as 1 by L, and this is square root of Vm, the plateau value, which decreases with L, but very, very slowly. And now you have three regimes. The instability control regime is still there, which we cannot say anything about. This is the regime where avalanches appear and the dynamics is ruled by the spinodal. We have this large region, which is a nucleation control regime, and then there's this plateau region. So the lesson from here is that if you want to get infinite solid characteristics from a finite computer simulations, you should not do it at very low strain rates, because then you will be entering into a regime which is dominated by finite size effects. So this is an important lesson. And here is the phase diagram. You have N crystal and M crystal. They are separated by a line of some transition. Okay. And it turns out this is a transition across which the intensive order parameter in the infinite solid, it has a change of slope. So this is like a third order transition, but locally the jump is very large. And for a finite solid, it appears as a standard first order transition. So this is very unusual. So it has mixed order depending on what you are looking at. Okay, so here is the droplet transition. So at this point, so this is the effective free energy as a function of the intensive order parameter. And at this point, the effective free energy has a sharp change of slope. And this is accompanied by a sharp drop in the stress. And at that point, these droplets appear, and you can see that each droplet is surrounded by a dislocation, which is exactly what you would expect from our Landau-Ginzburg theory. So here you see that inside the droplet, the order parameter is very large, but the stress is zero. And if you plot this, you will see that, this is oblate ellipsoid kind of thing, but it has only one slip plane, so it is not in the limit that we were talking about. And in order to get that limit, you have to go to very large system sizes, because each of these slip plane, each slip plane enters the system through a transition which is similar to this. So there are further minima which appear at larger and larger strains. Okay, so now we go into the structure of this droplet. And what we have done is to average the order parameter, keeping in mind that the shape is elliptical. So we average the order parameter inside this plane. And you can see that this is the black line where the order parameter goes to zero as you travel outwards from the center of the droplet. Okay. And if you plot the stress rises. Okay, so this rise and the drop are exponential, we could fit exponential and find out the penetration depth, and the interfacial width would be something like a coherence length. And if we divide one by the other, imagine that you are dealing with a superconductor. So then this thing comes out to be 1 over root 2. And people who are familiar with superconductor physics would recognize that this is lying at the boundary between a type 1 and a type 2 superconductor. The order parameter in the direction perpendicular to the droplet, that is very sharp. However, the stress has a much longer range. So away from the droplet, the stress penetration depth is large and the order parameter coherence length is small. So you are in strong type 2. So this is a very peculiar system where in plane you have an analog of type 1 superconductivity, whereas out of the plane you have type 2 superconductivity. So this is, so I am sort of somewhat before time, but then I'll go through the conclusions somewhat slowly because, hi Bulbul, questions?
No, not yet. You're in time. Yeah.
So let us go through the conclusions because I am sure that this was quite dense. So we started with a gapped excitation, gap because it is not a gap in energy, but a gap in the susceptibility. So we took these excitations, we took the most susceptible excitations, and we found that as a crystal slips, these condense on the slip plane in the quasistatic limit. In this limit, automatically dislocations appear in order to restore translational invariance. However, there is a topological shape constraint on the number of dislocations because the number of surface steps has to conform with the shape. The shape is the thing which we keep constant, so it cannot change before and after the transition. So this produces a constraint on the total Burgers vector, so, and which in turn limits the growth of the order parameter only to subdimensional domain. This means that the nature of ground state is very strange. It has strong ordering on the subdimensional domain, but a vanishing jump in the intensive order parameter. However, the intensive order parameter, it depends on the number of slip planes, which in turn depends on the strain. So intensive order parameter is proportional to strain after the transition and is a constant before the transition. So there's a sharp, there's a jump in the susceptibility. Okay, so there are other transitions which show similar behavior of the order parameter, but I don't have time to go into that. Now, if you have a large density of slip planes, then you can actually imagine critical droplets which have stress 0 inside, and they are described by a non-zero interfacial energy. So dislocations don't directly contribute to the droplet energy. I mean, they do, but at a subleading order. But they contribute indirectly because without dislocations, you would not have a stress-free droplet to begin with. Okay, so the quasistatic transition at 0 strain rate, it determines yielding behavior over a large range of timescales. Now the question is, where do we go from here? So plasticity theories, typically they involve only dislocations, but now we see that very naturally dislocations they couple to the interface dynamics. So we might be able to write down a new plasticity theory where the steady state flow of a crystal would be the flow of an extremely non-Newtonian but streamlined flow of something which you can call the gauge liquid, where the velocities will be replaced by the time derivative of this order parameter. So this is something that we are working on. Of course, this is a fluid where the viscosity, it diverges as the strain rate goes to 0, and because of this essential singularity. Okay, the question of glass. Does this NM transition survive disorder? I think Jürgen is going to talk about this at the end. And you can see that the first passage time that we calculated, that is also a prediction for the viscosity. I should have told you that, because it gives a time scale and we have the yield stress. So that gives you something which has the same dimensions as viscosity. So the question is whether it is singular or Newtonian in glass. So in a crystal, this is singular because you have this e to the power 1 by strain rate to the power 4 kind of singularity. Yeah. And then you have the question of active crystals. So, you could analyze active crystal dynamics using the same ideas. And we believe that instead of steady state flow, now you will have chaotic, turbulent flow, but flow of this liquid, which we call a gauge liquid. So this is more or less what we wanted to say. And this whole business, the whole framework was developed by these extremely intelligent students. And the beginning was done by Shashwati, who was also present for a long time. And then she, of course, is a postdoc now. The Landau theory was more or less completely formulated with the help of Pankaj Popli, who is really very fantastic. And finally, Parshvanath, he is a sort of genius with computers and also with analytic theory. So all of this was developed by these students. And of course, I cannot forget my colleagues, Jürgen and Peter, with whom we have almost daily conversations. And basically, this whole theory, as you could see, this mixed order was something very difficult to understand. And basically, I would say something which is nonsense, and then Jürgen and Peter would correct me, and this is how the whole thing happened. And I met Peter Solich at a KITP meeting, which I think Bulbul will remember. And we have been paid by several people, like the Dionikos EU FP7 collaboration. I spent some time in OIST, and then CSIR pays the salary for the students. Okay, some of the students. Thank you for your attention.
Thank you, Surajit. I'm going to collectively thank you for everyone. I don't see any questions in the chat. So for the speakers in this room, you can actually just unmute yourself and ask questions. I can start off, Surajit, by saying there's a lot of meat in here. So could you just take a minute to sort of summarize what's crucially different between the old dislocation mediated theory and what you're saying now?
Yeah. So first of all dislocation mediated theories, they strive to get a yield point which is independent of strain rate. We are saying that that is completely nonsense. Yield points are inherently strain rate dependent, and in the strain rate going to zero limit, the yield point of every crystalline solid is zero. Now this is something which everyone thought that this is just something where why we should bother about it. This is something happening at very low strain rates. However, what we show is that this quasistatic transition, which happens at strain rate going to zero, it determines yielding behavior over a large range. So this is basically our main results. Is this curve which goes through this experimental data. No one till now has actually even seen this, and this variation with strain rate used to be described in terms of dislocations, jumping over barriers, and so on. And you need to attribute certain properties of dislocations for this, so that looks a bit like this Platonic epicycles and so on. And we have this one theory, which is extremely simple, and that goes through this entire data. Now, of course, this theory depends on the fact that there are these droplets. So, what kind of droplets? From where does it come? And that leads us to this new calculation of this droplet energy, and showing that stress-free droplets are produced automatically. Now, here I want to make a small statement here that normally, when you divide fluctuations into smooth and singular, you have already coarse-grained the displacements into a displacement field. So you have actually thrown away all non-affine displacements. So you have assumed that displacements are smooth. And that is why you get into all these problems of core energy of a dislocations and so on. So here we are introducing a little, small part in this jigsaw puzzle, where we are saying that don't do that. You divide up the displacement into affine and non-affine. And as soon as you do that, dislocations, you don't have to bother about dislocations. They appear automatically when any non-affine displacement, it condenses. Actually, this is far less mysterious than what looks like. So you have a condensation of this non-affine mode. This breaks translational invariance. The gauge fields, what they do is that they produce local stresses which restore translational invariance, and at the same time produce dislocations. So this whole thing, which is there in Herth and Lothe or any other dislocation book, is contained in these equations. So that is our main result.
Okay, I think we are out of time. Is there any burning question from the people in this room? If not, let's thank Surajit again and move on to the next talk. Thank you, Surajit.
Thank you.
So the next talk, Desh, if you can set up